Just forget that. I wanted to resume chapter 21. I've got some more images. This is based on the lecture from yesterday. No, last week. Whenever we started this, I'm so confused. We're going to talk about, well, a lot of the things. Some of the things we already talked about. We'll just quickly review reverberations and comet tails and ring downs and shadowing and edge shadowing, which is really not the same as shadowing, although it still produces a shadow. Enhancement. And then we'll do another one called focal enhancement, which is, I really don't even think of as an artifact, but fine. Mirror image artifact, which are really cool. Speed error artifacts, which are pretty cool. I'm going to add one that is not in the book, and I don't understand what they're thinking. It's a really important one. It's called twinkle artifact. We've already talked about, but we'll do again, side and grading lobe artifacts, refraction, which is also, that's a really cool one. Slice thickness, we've kind of spoken about that already. And lateral resolution, lateral resolution, I don't see how a lack of resolution is an artifact, but if that's what they want to call artifact, that's what they call. That's probably about as far as we'll get today. So without further ado, let's kind of zoom in on today's stuff. Remember, we don't need to go over hypo, anechoic, isochoic, homogeneous, and all that stuff. Just quickly talk about these assumptions, because Edelman likes them. Edelman likes assumptions, and he likes breaking assumptions. So sound only goes in a straight line. We assume it. The machine has to assume it. Doesn't always happen. Echoes bounce straight back. Not so much always. Sound always travels at 1540 meters per second. Nope. Reflections are only from the beam. Nope, unfortunately. Imaging plane is very, very, very thin. It's not. It's actually probably thicker than the width of the beam. And echo strength perfectly demonstrates reflector. Oh, I must have covered that up. Reflector characteristics. And if we have anything wrong with our TGCs, which we always have something wrong with our TGCs, then that is not perfectly done. Okay, and so then we spoke about reverberation. An important thing to note about reverberation, let's just put I'm going to put a line here of something, let's say fascia. Let's say it's like a really bright muscle fascia. And this usually happens with bright echogenic barriers or interfaces. Because why? Because they're probably bright because they're reflecting a lot of sound. And if they're reflecting a lot of sound, we start to notice things that we otherwise wouldn't notice. And so sound can come down and back like it's supposed to. Ugh, that's just ugly. Let's do that. Goes down, echo returns. That's normal. And then we see that line because that's what we do. But then it bounces again off of in this case, the transducer itself. Reverberation can happen between an interface and the transducer, or it could happen between two interfaces deeper inside. But in this case, I'm just making it super simple. And then this comes back down and creates another echo. Well, it took time to do that. So then it's going to put in, I'm going to change the color of this line. that extra time, it's now listening to echoes that have bounced back and forth twice. Therefore, this line is twice as far away. So if you think about what it, if you're wondering if you're looking at a reverberation artifact or some other kind of artifact, one thing to note is that the distance between here and here will be the same as there to there, and will be the same if you can see a third one. Reverberations occur in not randomly, but in very much the same distances. So in this case, it's a, let's just call it fascia. Doesn't have to be fascia, but that's what it is today. Connective tissue. That distance between the fascia, and then it bounces back up to the transducer, bounces again. We see that, and then we see that line, and so on and so forth. Oh, and I grabbed a nice image showing this. Now this image is so close up, it's really hard to see what I'm looking at. It's not even sure this is human. A lot of times when I find things, it's veterinary ultrasound, but this appears to be a close-up of some kind of, tissue here, and then down in here. I think this is air in the GI tract somewhere. That's what it appears to me to be, but we could see that each one of these is equally spaced. It starts to get blurred out and weaker, but there's an even spacing between because, well, what exactly is happening here? We're seeing, this is the original true echo. It seems to be bouncing back and forth between something that's, well, if each one of these is that long and that long, there seems to be something that's just off of screen that's initiating this reverberation artifact. So that's the only problem with this picture, is that it's not showing both surfaces. In any case, great reverb artifact. And then very closely related are the comet tail and ring down. I've already mentioned that in my book, comet tail peters out quickly and ring down goes all the way through. But they are both essentially reverb artifacts. So that's a nice shadow. Where's my, okay. I mentioned a gallbladder. This is a liver here, gallbladder there, and we have this little guy there. We call that the comet tail. I call that comet tail. So I call that a comet tail. I call this one going all the way down. If we could see more of this picture, it would go further. Ring down. But they're both under the subheading of reverberation. The reason why you don't see individual lines is literally because the lines are so close together that you can't see them. They're just totally smoothed out. In other words, the reverb is just bouncing back and forth in that tiny little spot within, that is air, by the way. I know it's air because if I have this is this is once again, this is a gallbladder. This echogenic structure here is outside of the gallbladder, and it's posterior to the gallbladder. Well, I just happen to know that that's the first part of the intestines. Is usually right there. It's called the duodenum, but it's, I know from experience that this is GI tract here, and we're catching just a little bit of air, and that's causing the ring down right there. Okay. Moving right along. I think the next one is shadow. Yes, the shadow nose. I don't have a picture for this. Well, that's okay. I will write something. A shadow, just a regular shadow. There's edge shadow, which is very different. But a shadow is, quote, unexpected, high attenuation. That's in here. Here's the, we can get that quote from the book of Kurt. All right. So unexpected high attenuation. There's two different things that can do that. One is increased absorption. Absorption is generally heat, although we're not really heating anything up because it's not enough power to, I mean, yeah, we could heat things up, but it's very minimal. So unexpected absorption or reflection. Maybe a combination of both too, but it's usually one or the other. Unexpectedly high attenuation. So let's just come down to this first one. I mentioned the other day, breast ultrasounds. If you find a lump, we find lumps all the time in the breast. Most of them are actually not a problem, but sometimes we do get concerned. This one is very concerning. It has a pretty dark shadow. We don't like to see that. The tumor itself is, well, it's obviously we know that's the top part of it because the ultrasound beam is going down, hitting it and reflecting like it normally does. But then we don't know, does it do this? Does it do that? You know, we just don't know because of this would be high absorption. Sound absorbed. Some of it was reflected. Here, let's get rid of that. There we go. Some of it was reflected, but we don't really have very high, like evidence of like very high reflection right here. So this was absorbed sound, and therefore there's no info inside of the shadow. That's what a shadow usually is. It's either zero or a lack of information. Let's see, I have another shadow. Down, yes. I liked this. Oh, urinary bladder. Yeah, well, that makes sense. Not exactly sure how someone got a stone this large on the urinary bladder. Oh, it must have formed in the bladder. It couldn't possibly have come from the kidney down at that size. This one has very high reflectivity, as could be noted by this very echogenic wall to it. So when we see that, the reflection or the high reflection doesn't leave a whole lot of sound energy behind because it's all been reflected. So that's another way of creating a shadow, is by reflecting. But in either case, it's all a part of attenuation. So once again, 0 info back here. What's interesting here is that we do have another little structure. And a tiny amount of shadowing relatively. Let's see, that's direction of sound beam. Yep, that's the shadow for sure. So whatever's creating, whatever's structure, whatever these two structures are, they're not the same. Obviously, they're not the same size, but they're not the same consistency either. And that tells us something, you know. Maybe this guy is older. Question mark. That could just be older. Maybe soon enough, sooner or later, there'll be a stronger shadow behind that smaller object inside the urinary bladder. I think I moved enhancement up one because enhancement seems like it makes a lot of sense to talk about after shadowing, because it's the opposite. A shadow is unexpectedly high attenuation. Enhancement is, whoops, unexpected low attenuation. Whereas in the shadow, there's a lack of information because of the unexpected, because the attenuation took so much of the energy away. It has low information or perhaps no information coming from the area of the shadow. This area of enhancement, once again, this will be a curt quote. Too much that is curt. Don't think that's kind of just my way of explaining it. There's too much information. That's the strength of the echoes are unexpectedly high because the attenuation above it was unexpectedly low. So the beam's too strong. Or at least it's too strong in the sense that the ultrasound machine can't figure it out. So that was enhancement. Edge shadow is a shadow, but it's completely and utterly different. When a beam of sound hits the edge of a rounded, this always happens on rounded surfaces. On the edges of cysts, actually. On this cyst, I could actually draw, if I wanted to, little edge shadowing. It happens with rounded surfaces. I don't want to draw it because I've done it before. It's a little complicated. If I get it wrong, I get it wrong. But basically, there is a speed of sound, C1 does not equal C2. The speed of sound changes, and as it goes through a curved surface, on the edge of that curved surface, we simply notice that there is a change in direction because, remember, if the sound beam hits a surface at an angle, it will, and there's a change in speed, there will change in direction. It's refraction. Let's just quickly say this. If I, my sound beam comes along here, any refraction that occurs is so minute that it's completely we won't be able to see it. So this goes through, sound continues to go through, come along. Is there the slightest change in direction? Yeah, sure. We'll just say that this is very slightly changed, but you also note, well, I didn't even really draw it that way. It's hard to do. It's hard. Okay. Very, 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 very slight change in direction. And the beam is uniformly changed. It all changed direction. But on the edge, part of the beam went straight. Part of the beam was refracted, but it's still one beam. So our area has increased. Intensity of the beam cannot stay the same if it's widening out. And so instead of the beam staying relatively in a narrow laser-like fashion, it spreads out. The area spreads out, intensity goes down. Intensity goes down. And therefore, echoes go down as well. The strength of the echo is directly dependent on the strength or the intensity of the beam. So by spreading that beam out, we're making it weaker, and the echoes are weaker, and it creates an edge shadow. Depending on the structure, depending on the speed of sound, that edge shadow is sometimes very straight, like this one over here that I drew, just like straight on down. But I've also seen them a little more wedge shaped. And that seems to be the difference between whether or not C1 and C2, which one's faster, tissue 1 or tissue 2. And that seems to have a difference in exactly how these spread out. And I think I have a picture of this. Yep. In fact, let's draw, if I could do this without messing up. There's the beam line, of course, not nearly as bright as I wanted it to be. And then there it is spreading out. So the beam just, actually I'm gonna do it a little more accurately. Yes, that's a little more accurate. Okay. So that beam line is just hitting the edge. Part of the beam goes straight, part of it goes through the fluid of this cyst, and direction is changed. Okay. Trying to make sure I don't say anything incorrectly here. Okay. Next one is new. So I'll slow down, although I don't really like this. This is my least favorite. One of my least favorites, because it's so easily fixed. Well, we were just talking about intensity of the sound beam. And the more narrow the beam, the higher the intensity. The higher the intensity, the stronger the echoes. So if I'm going to draw, let's say, a single beam in here, remember, many ultrasound beams create one picture. Okay. I have my focus here. My focus is right there. Therefore, my intensity right in this area is going to be a little high. Most of the time, you don't notice this, but every once in a while, I guess it is possible to have an area of focal enhancement. So here's this whole area here where it's a little bit too bright. Well, if I could draw the ultrasound beam in, jeez, I need my little cheater here. That's where my focus is. This is where my beam is strongest, not including attenuation and all that, but just in theory alone, that is where my beam is strongest. And of course, that's where my echoes all along this line, that's where my echoes are a little bit too strong. And so, of course, we just fix this with TGCs. Oh, by the way, just so you know, I forget, you guys haven't been through so many of this. This is a liver. This is the gallbladder here. A little bit of intestines in the area too, but this whole thing here is liver. Okay, but you will be covered in that soon enough. Plenty of liver images soon enough. Okay. So speaking of livers, mirror image artifact. Oh, yeah, I should have. Enhancement, mirror image. So we need to talk about something. And the diaphragm is usually the example given. Not always, but usually the example given of what's called a specular reflector. A specular reflector is something that is, specular is like mirror, specular is mirror-like reflector. That's right, I think we did talk about that. That means sound really bounces off the surface. Now, the diaphragm in and of itself is a specular reflector. It's very smooth, kind of like a mirror. Not to mention, right behind the diaphragm is lung. So you have air. So even if sound gets through the diaphragm, it's bouncing off the air of the lung. So we don't see lungs normally. Lungs are completely gone or completely out of our ability to see unless there's fluid in there, which is a problem. Okay. sure I do this right. Yes. So I'm scanning along on this person's abdomen. There's my transducer. And I send a beam of sound down. Let's make a nice color, green. Beam of sound goes down. Always the wrong color. Actually, I'm going to have this beam is steered a little bit just to help my. The original beam goes down. All right. Here's the problem though. It hits a specular reflector. Pretty much 100% of the sound bounces off. Some of it bounces back to the transducer, but a large amount of it, because of the angle that it is, bounces off in this direction. Well, and there happens to be a mass in there. All right, fine. Well, sound then bounces off. Let's do a different color for the bounce back. So the echo goes back, bounces off the same surface, and goes back to the transducer. Okay, so we know there's going to be an artifact. We know it's called a mirror image artifact. Where do we now find this mass? The machine can't possibly know that sound did not travel in a straight line. Machine also knows how long it took for any echo to come back, because it sent out one beam and it waited for the echo. So all of this back and forth here is extra time. And what do we know about time? Time is depth when it comes to ultrasound. This is a range finding machine. It precisely times from the pulse to the echo. Every 13 microseconds is 1 centimeter. So if it took, let's just say another 13 microseconds for the sound to bounce back and forth right there, so that'd be kind of 1 centimeter away from the specular reflector, and the machine can't possibly know that that's what happened, it's going to think and of course, I didn't give myself a lot of room. I'm going to get rid of this person's back here. Shoot, I'm just going to get rid of specular reflector as well. Okay. Oh gosh, what color is that? Now I know what the color it is. Whoops. Oh well. A little bigger, but perhaps it got distorted. Does that make sense? This is where the machine sees that mass, because it doesn't know. It is completely ignorant. Wrong pen, wrong color, wrong everything. Oh, and of course, the machine thinks that the beam is straight. It thinks the echo is coming from that spot. Now, what we see on our screen is both this, the fake, and this, the real. Well, why do we see the real? Well, because not every beam is doing this. We'll have another beam of sound a little bit later on. Let's remember I'm steering, or I'm using a curved perhaps, or I'm steering, whatever. Then I have another beam of sound that comes down and a reflection that goes back. And so that beam and that reflection there's nothing wrong with. It was the original beam and the original reflection that there's a problem with. And so, but both are displayed on the screen, of course, because there are hundreds and hundreds of scan lines, scan beams creating every image. Some images, some beams are wrong, some beams are right. So we get both wrong and right on our screen. Let's see, I've got a unbelievable image here. Yeah, and there is distortion, so I think my picture was pretty good. This has got to be a child. I think I actually saw an age. No. It's got to be a child. It just, children are sometimes scan beautifully when they're not wiggling around. Oh, you can see someone used their body marks. I'm not a big fan, but whoops, I just saved. All right. So this is our specular reflector. Yes, it reflects sound. There is nothing all in back there. That is nothing. Just like when you look at a mirror, you can't see the wall behind the mirror, but you see yourself. This is the wall behind the mirror. There's actually nothing there, but we're seeing this guy is now reflected there. Let's see. God, some of these I can't even figure out. Some of these objects are so far away that they're not even displayed on the original picture. It's like they're literally bounced from like an object that's all the way over here. Does that make sense? This is, I love this one. And we see this all the time. We see it all the time in the liver. And of course, when I say nothing, this is actually, that's lung space, like here, and then back here. This is actually the bed. You know, the person's, this is their back. But anyway.
So will you always see the mirror plane there?
Often see the mirror. Sometimes we don't, but we very often do. And so you just have to, you know, you have to recognize it. We'll definitely see it when we next semester when we get in the lab. Some of you will show this beautifully, some not. I really don't know why some people will not show it more beautifully. Okay, I know, it kind of looks like I was drawing glasses with spots on them, but no. No, actually I have, oh, this is another cool one. I like the speed error, creates some cool effects. So once again, I have, let me write some things down here. This is lung. Also, we could also call this the pleura or pleural space. This is liver. And here we have a fat tumor. Speed of sound is 1540 meters per second, right? That's what we always, always, always have to assume. So what if we violate that rule? So let's say we go through the skin, the subcutaneous fat, and then gets to the liver. Let's just say that that's all really close to 1540. So beam comes down. What color should my beam be now? Nice and green. And that's traveling at 1540 meters per second. That's what I get for trying to fix my S. Okay. But fat, what do we say about fat? You don't see a lot of Olympic sprinters who are fat. It's just true. Fat tends to be slow. So let's use purple in here, and I'm going to continue my line. Sound continues through. But at this point, it's slower. So, you know what, I think, well, let's just say, no, you know what, I actually have I can't remember what the value is, but I do think it's actually written there, 1450, okay. That's what I was gonna guess too. Should have just gone with it. 1450 meters per second. And then we'll go back once again. To the original 1540. I'll go ahead and I'll write that in. 1540 meters per second. Okay. So the speed of sound changes a lot, but it's usually not dramatic. And if it, well, I mean, you can't really go into bone anyway, so that would be a dramatic if we could, but we don't. Sound's reflected anyway, so we don't really see the effects of what bone can do. But a decent sized fatty tumor in the liver will cause a problem. Remember, we're saying 13 microseconds per centimeter. And down here is 13 microseconds per centimeter. But here, if it's slower for 1 centimeter, it's going to take more time. I don't know what the real number is. We'll just say, we'll just make it even and say 20 microseconds per centimeter. Because it's slower, it takes more time. Well, if you remember my illustration for attenuation, and especially like attenuation with posterior enhancement, we violated the rule of how many decibels per centimeter. And by violating that rule, the computer didn't understand what happened, and it just said, oh, it must be that these echoes behind this structure are brighter. Well, they weren't, they shouldn't have been brighter. It's just that we violated the rules and we messed with the TGCs. Now we're violating with the speed of sound rules. So if this is slower, the overall beam from the very top to the very bottom and then back, because this is going to happen on the way back too, right? It's going to be a double whammy. There's going to be echoes, and then there's going to be an echo going through their way. So this happens twice. If the beam overall is slower than expected because of this fat tumor, and this is a range finding machine, the machine doesn't know that the beam was slower, what's going to happen to these echoes back here? If it took longer for the echoes to come back, it must be that they're deeper, right? Longer it takes for something to come back, let's try. Well, I guess I'm just going to have to erase that. Well, that's kind of cool. That actually looks like I shifted it down. Everything behind that is placed a little bit. It's misplaced because the echo took longer to get back. Obviously, according to the machine, obviously it must be coming from a deeper place. And here we have that once again. The liver, for the most part, is 1540 meters per second, like it's supposed to be. The fat was 1540 meters per second. And now this line, which should have been continuous, is broken. It seems to be rather, oh, here's another picture. This is a famous picture, this top one, because it's just so blatant. It's usually not as blatant. And this is a good example of one that'd be a little harder to recognize. Let me first draw in this back border. Should look like that. But instead, it's got this nice smooth, and then suddenly, boom. It's doing that. Why? Because you have this tumor up here. Speed of sound is slower. In that. And if you look at kind of the curved surface, so beam lines, sure enough, are going through there. And there was a little bit of a distortion here, but this beam line went through more of the mass. So there's more of a distortion here. This beam line went through quite a bit of that mass as well. There's more of a distortion here. This beam line only went through a small amount of the mass, and so there's only a small amount of distortion here. And once again, this is liver. That's a hard, that's because of the tumors, really, that's a hard image to even understand what we're looking at. Okay. Oh, and rarely, it's possible, but I don't know that I've ever seen it. It's possible if this was faster. And the stuff behind it could actually be lifted up towards the transducer because the overall beam velocity, if you average the entire velocity, seems to have gone up, or at least in the far field of the beam, it's gone up. And therefore, obviously, according to the machine, these echoes must be closer to the transducer. Like I said, though, I don't know that I've ever seen that. It always seems to be slower rather than faster. Okay. What time is it? Oh, that's right. I got my alarm set. Oh, we're doing really well on time. Perfect. Twinkle, not in the book. I don't know why. Twinkle artifact is one of the most important, useful artifacts that you could think of. Now, I drew a gallbladder, but I have a picture below of a kidney. Let's start with the gallbladder. Twinkle artifact is, we used to think of it when it was first noted, it was thought to be a color version. In fact, let's make sure I put a little color box on this. Okay, there's my color box. They used to think of it as a color version of reverb. You put Doppler on and the Doppler is reverberating back and forth and it causes twinkle. And honestly, if that's the way you think of it, fine. It's not going to hurt anything. It's just that's not what's really happening. What's actually happening is it's something about the way the Doppler interacts with usually calcifications, although it could actually, no, calcifications in air. Air will cause this too. So I guess it's more of a, I don't know how do you actually, because I'm beating around the bush here. The engineers say that this is actually something that's happening inside the electronics, but it happens with calcifications, it happens with air. It happens with metals. If you have like a tiny piece of metal, a BB, for instance, embedded in your butt, one way to prove that it's there is to use Twinkle artifact. So anyways, you put color on for Twinkle artifact, and what you end up seeing and let me use blue in here as well because it's a mosaic. You get this mosaic of color behind these structures, and it's really useful. Gallbladder, somewhat useful. It's useful, but I would say somewhat useful. It could tell you the difference between echogenic sludge. By the way, sludge is something, it's like a thick liquid that we can see. A lot of cholesterol and salts and stuff are in there, and sometimes little cholesterol crystals can cause can get in there. But if there's tiny little calcifications or tiny little stones of any kind, it will create this artifact, and it kind of tells us, it says, okay, this isn't just sludge. This is sludge with tiny little stones in it. Probably a better use for it is in the kidney. So a lot of people think kidneys are easy to scan. They are not, they never will be because of this. Without, was putting my hand over the screen so you couldn't see part of the screen. Whew, I wonder about me sometimes. Imagine you can't see the picture on the right, and all you see is this grayscale image of the kidney. Where is the stone? Kidneys are like Oreos. They have a kind of a chocolate outside, echogenic inside, creamy on the inside. And the problem with that creamy on the inside, the echogenic inside of the kidney, is that it could very easily hide. It could very easily hide stones. Now you might be saying, but Kurt, you told us that stones shadow. They do, unless they're so small that the beam actually envelops the entire stone, then there's no shadow. So very, very tiny stones will not shadow, but they will twinkle. Now I'll tell you, probably because everyone uses this book, not a lot of sonographers use this anymore because they're not being taught it anymore. So this is definitely something you want to be able to know about. I've had radiologists who didn't know about this either. But you could see, when you look closely, this is a mosaic of colors. I actually have a little note in my book. It says the intrinsic machine noise of unknown origin is a definition I got from some book or some article somewhere. But like I said, if you just want to think of it as Doppler reverberation, think of it as Doppler reverberation. That is fine. Let's see, so speed, now I added twinkle. Okay, the next 10:30. The next one or two, actually doing pretty well here. At least I'm doing well. I don't know about you guys. I'm feeling great. Lobe artifacts. I've already mentioned this before. We don't need to spend too much time on it. What are we violating with lobe artifact? That every single object that we see is inside of the beam. Right? Everything's got to be inside of the beam because the beam is very, very thin and nothing ever happens on the outside of it unless it does. And so if we have let's just do it. Happy time. A nice bright object out here. Let's just say this is like, oh, you know what's a good one is bladder wall. You know why the bladder wall? Because that too is a specular reflector. Specular reflector, 100% of, close to 100% of the energy that hits it bounces back. So if you have a bladder wall outside of the beam, but inside of the grating lobe, that's going to create an echo. Machine doesn't understand that. Machine thinks the echo came from here. So that's where it puts it. Machine can't know about that. And so what do we have here? I chose this one because this is really good. This is, oh, okay, I know what I'm looking at. This is ascites. And looks like loops of intestine. But let's see, what do we have? We have more loops of intestines. Oh, and we have, yeah. Okay, I see what they're saying here. All right, well, let me do these loops of intestines first. This is very confusing because a lot of people, including myself, and probably mostly myself, which is why I say a lot of people, feel like side lobe artifacts always has to mean that whatever these two structures are here, well, they're in the side lobe, they're outside of my beam. That must mean that they're over here, totally outside of my screen or my field of view. No, that's not how it works. One beam comes down, it has side lobes. And then another beam comes down and it has side lobes. So these side lobes can occur from structures that are in your screen. They don't have to be like out of sight. So now having said that, I'm still not sure where exactly these are coming from. So you have a structure here, you have a structure here. Well, I guess that's the bad part. And that's actually, this isn't unusual. This kind of artifact can be very difficult to identify. When we look at that, we could say, oh, that's just like blood inside of the ascites and it's settled out. And someone else might look at it and say, oh no, you're right on the edge of some intestines. So it's edge artifact or slice thickness artifact. And others might say, well, no, it's side lobe artifact. And others might say, well, no, it's just simply noise. And it can be very difficult to understand where exactly everything is coming from. Do I have another? I don't. Okay. Your book, actually, what your book has? Yeah, your book has, God, a real horrible picture on page 367, but it's showing a green beam line and a blue, I'm assuming the green line on the side lobe is blue. Yeah. A main green line, one beam line, guys, not the whole picture, one beam line, plus one blue side lobe. That side lobe is hitting something really bright. So even though it's a weak lobe, that surface is so bright that it's sending echoes back. The machine doesn't understand that, so it puts that almost like a continuation or a ledge out into well, we're going to call it bladder. I'm not even 100% sure what I'm looking at on that picture. Side lobe artifacts are oftentimes seen more likely inside of fluid. Well, why? Because there's no other echoes competing with them. So you have this bright echo outside of the fluid, nothing inside the fluid, so it's just easier to see. That goes with a lot of artifacts when it comes to fluid. Refraction artifacts. Now this one I like. I got to make sure I draw this correctly though. We can see this. I guarantee you, someone in our class next semester will be able to see this. One place that we oftentimes see this is in the upper abdomen, and we have muscle. Whether you have a six-pack or not, everyone has a six-pack. It's just how much insulation you have over it. That's the question. So the rectus abdominis muscles, they come in, and this is going to be similar to edge shadowing in that it's a refraction. Edge shadowing is a refraction artifact. Refraction is a refraction artifact. So as sound beams come down, they're going to hit, it's usually a curved surface. Let's see, so sound beam comes down, hits this curved surface and makes a bit of a turn. Echo goes back, turns again, goes back to the transducer. And like the mirror artifact, it's going to misplace these echoes, but it's not mirroring, it's refraction. Now, with mirror artifact, there was a time delay. Therefore, the fake information was deeper. This time, the fake information all right, close enough. A little bit bigger, but that's okay. This time the fake information is side to side because there's really, the amount of time lost here is it's not even existent. It's so negligible that there's really no time difference. But what the transducer thinks happened oh, by the way, this is the aorta. Did not tell you that before. So we very oftentimes see this, and someone will have two aortas. And you put, okay, it's time to switch over, but you put color on and there'll be two Dopplers of color. So this happens a lot in the aorta. It also happens, this happened to me, I can't remember if I can't remember, I was a new tech. I can't remember if I figured out the problem before or after I got in trouble. But rectus abdominis, these muscles, this 6-pack, it's really more like an 8-pack because it goes all the way down to the pelvis. And in my case, and in quite frankly, a lot of cases, I'm not the only person this has ever happened to. Rather than oh, that's good. Rather than one early pregnancy, I was like, oh my gosh, you have twins. One's larger than the other. There you go. You have twins. Yay. Nope. Rectus abdominis muscle refracted the sound beam, hit one early pregnancy, like just like a gestational sac, maybe a tiny little rice-sized baby inside of it. But I ended up seeing two. Oh, and I guess the other thing to say is, once again, why do I see two? Why don't I just see only this one? Every time, Kurt, every time. Why not? Oh, there we go. Why not only this one? Because this one might be the fake, but not every beam is faked out. The next beam that comes along creates correct information. So we will end out having fake, and real. Cool. Actually, oh, there's just a little, that's right. I have a little picture of it. And yes, this person seems to have 2 aortas. And rectus abdominis causing the problem. But man, if you didn't know about this, this doesn't happen. Let's see. It happens, but it doesn't happen all the time. But when it does, you just have to be prepared for it. And that's why we learn about this. So we can be prepared. And you don't tell the doctor that the person has 2 aortas. Because things like that happen. Actually, like duplicated vessels do happen. Let's see, you gotta be careful. Let's see, the last one. Yeah, cool. I didn't want to talk about that today anyway. So you guys are cool. You guys want to talk about the test?
Yes, please.
All right.